I should probably preface this a little bit. So again, I've known Michael for, I don't know, like 17, 18, maybe close to 20 years now, probably close to 20 years. And you and I have spent probably over 100 hours, maybe hundreds of hours on the phone. And so you walked me through all of this. So I would say that you've done a ton of independent research, right, with folks like Ari de Geis, who have been out there developing their own theories and models. And so when you talk about beta voltaics or the plasma vortex, it's kind of like drinking from the fire hose because there's so much all at once. So I just wanted to kind of get that out there and let everybody know there's a lot of depth to what Michael has done.
Sorry, folks.
Oh no, you're fine, sir. Okay, so let me see. I had hands up and then they disappeared. I want to see hands up again, guys. And of course, the minute I'm asking for hands, they disappear.
Hey, probably everybody went for a bathroom break after my long rambling.
Now, there's Harold. Harold, go for it, sir.
Yes, I kind of got curious about your explanation on potassium 40, about how rare it is. Tell me a little bit of the history behind that discovery of the potassium 40 and your conclusions about it.
Not my conclusions, just to give credit where credit is due. Ari de Geis wrote about this a long time ago, and he was not the first person, but he noticed from the satellite data when they were doing experiments in, I think it was the WISE satellite. I could be wrong on the definition of that, but it was it's one of those nomenclatures that is hard to remember unless you're sitting there looking at it. But it was a satellite that was looking in the ultraviolet spectrum. And when they started looking at nebula in the ultraviolet spectrum, which you cannot see on Earth. So none of this data existed prior to this satellite data. But he had hypothesized that the plasma vortexes that were created in in supernova explosions, that there was a certain part of the creative process that was happening in those compressed vortex rings as these stars were dying. A lot of elements are being generated in the death of stars. And once he had the satellite data, he could see that there were several lines for potassium 40 in the spectra. And so now with this information, he started looking at his hypothesis again, and he realized that if it is the plasma vortex is where it's happening, and it's because the vortex is compressed and it has the correct elements, a certain of the number of light elements that are in the cloud around the stars as they collapse, that as those stars collapse and the outer gas rings form and press away in the shock wave, that generates a lot of creation of materials that didn't exist prior to that, because there was nothing in the universe to create that prior to that. So these particular elements and these particular isotopes are generated in these supernova explosions that didn't exist prior to that. And of course they go all over the universe. I mean, they go all over the galaxy, and well, specifically, I don't know about between galaxies, I don't know what's going on there, but what we can see in the radiation that everything emits is that there are spectral lines that are in the target vortexes that are coming off of these collapsing stars that showed the lines for potassium 40. And so he generated his first devices based on that information, and it wasn't very long. It was like 2 years after he started his experimentation that I was trying to get a license from him for that technology for the plasma vortex, so that, in my eyes, it was a way I could generate a very valuable isotope, potassium 40, in large quantities. I mean, in purities that I'd never seen before. I mean, no one's ever seen it. The samples that I saw were as high as 97% of the sample was potassium 40, and potassium 40 in nature is so small that the best they can concentrate it, like if you go to an isotope concentrator and they're using like, what do you call it? Gas cycle. I can't even think of the terminology right now because I haven't used it in a million years. I can't think for some reason. The same type of way that they isolate a lot of isotopes is they bind them to noble gas, like and then concentrate it through centrifuge. There it goes. Finally got the word out of my brain. They use like centrifuge separation to get the potassium isotope in nature from 0.00017 all the way up to 0.3%. So the highest concentration you can buy of this radioisotope, this particular, potassium 40 isotope, the highest concentration you can buy on Earth is about 0.3%, which is a very, very high amount of effort that they had to go through to get it from its nearly, infinitesimal amount up to a level where you can measure. So when I told him that we could produce 97% potassium 40, and I showed him the spectrum and the volumetric data, he was just like, yeah, I mean, let's do this. I mean, because nothing like that existed prior to that, because we synthesized it. This was the first laboratory synthesis of potassium 40 in the history of the world, probably.
Oh.
I mean, as far as I know.
That's impressive. That's very impressive. So in the experiment, this is a transmutation process by which potassium 40 or is that potassium 40 a catalyst to synthesize, to get other element going? Which one is it? Is it transmutation or a?
It's a transmutation.
Okay.
It's a transmutation that's generated in the collapse of stars, and it's generated through the plasma vortex. There are other things that the plasma vortex can synthesize, but because of those spectral lines of the potassium 40, he came up with the hypothesis that it was the beryllium that is consumed, and that's why there's that dip in the abundance curve with beryllium at the very lowest point in that dip in the abundance curve is because it's used in the nucleonic synthesis of a lot of other elements.
Oh, okay. Well, that's one historically good explanation. Interesting too. Thank you.
You're welcome.
Awesome. Okay, let's go to Michael Boyd next, sir.
Hey, Mike, I got a question for you. Is this something you think you could do like thin films of? Why couldn't you do this at the micro scale? In other words, making layers of this stuff instead of just like I mean, if it works in a nuclear star, why wouldn't it work at the tiny scale too? That's my question.
That's exactly what I'm working on right now. That's precisely what I'm working on is getting it down to the smallest scale possible. I don't know if you've looked at any of the stuff that I've provided, but that device, it was using, I think it was about a 85-gram anode. And what I was thinking was to take that anode and split it down into a lot smaller levels and make much smaller vortex tubes, that are at like, the very, very smallest scale I could possibly come up with. And for a number of reasons, economy of scale, because if you can do a lot of these very small, very cheaply, then it would give me the ability to produce a lot of the isotope very quickly, instead of running one big thing and having a lot of waste and a lot of burning. But one of the impressive things that got my attention was the nuclear level of energy that we were seeing, which was, from the transmutation of the elements. It's not like a hydrogen helium type of thing. It's not a hydrogen or a hydrogen helium or a hydrogen lithium, type of level of event, but it's still significant heat gain, that I would have a workable amount of heat that I could continue the process without, especially at the microscale, because, and well, now I'm splitting off into a couple of different thoughts. Ari DeGoss also did some very interesting and probably what's going to be found to be pivotal exploration of converting Brownian motion into usable electrical energy, which has just been done like 2 weeks ago. The first experimental information, and they were doing it at the microscale, at the nanoscale, like you're talking about, in graphene. They had graphene samples that they were able to put an electrode on and hit it with a small amount of resonant frequency energy to the AC pulses that they were seeing going on. They were noticing that, I don't, if you ever looked at graphene under SEM or TEM, it essentially undulates continuously, and that is the Brownian motion moving through, the electrons, which are free in the graphene. If you're familiar with the formation of graphene, there's always two electrons, that are moving around in each molecule, between between all the molecules. There's always a bunch of extra electrons flowing around. That's why they hypothesized that they could get superconductivity and magnetism out of graphene prior to when they were actually able to do it. Now, of course, they've experimentally done both of those things. So now, just recently, like a few weeks ago, they were able to take basically make a nano tank circuit and be able to, take the, by adjusting the diode, brain breakdown again, by changing the resistance on the diode, on a extremely small scale, they were able to make squeeze a few electrons out of it. So they had an AC circuit, a tank circuit, and they're able to slosh a little bit of extra electrons out of it in the graphene, from the graphene, and just from converting Brownian motion directly into electrical energy through a circuit. And Ari DeGoss actually built things on a macro scale that were able to do that same thing. They were able to use that same, force of nature, but using a resonant frequency on like a very thin layer of copper, was the ones that he and I played around with. He basically took very, very thin sheets of copper and he put them between magnets in a big, and creating a very large magnetic field on the edges of a very long piece, very wide piece of a conductor like copper, and then hit it with a radio frequency, an RF frequency, that was at a resonant frequency that, you know, he just played around with it. And when he got the frequency where it was producing some electrical energy through the diode, he was like, okay, we've got some energy here. And he couldn't sell that one to me. I wouldn't buy it because the device was so large. I was just like, well, we're not getting enough usable energy. But, you know, he was trying to explain something to me on the micro or nanoscale that he was able to get some gross amount of energy at a macro scale by utilizing that same thing that's happening on the nanoscale, you know. So he was ahead of his time there, and I didn't understand everything that he was talking about. His math was way the heck better than mine. You know, he kind of stumped me quite a few times. At least he didn't invent his own math like Dr. Santilli did.
Well, thanks for answering my question. I appreciate it.
Did I answer it? I'm not even sure.
Yeah, I think you did. You
Okay.
basically said that's what you're looking for. That's kind of what you're researching yourself, is doing it on a nanoscale. And
Well, now that they can convert Brownian motion into electrical energy, and they've shown it, and I mean, it's reproducible, and directly from just the Brownian motion on graphene.
What you're
If you add, if that graphene was made out of carbon-14 and it was formed into a diamond that was composed from sheets of graphene and compressed under, you know, pressure, now you'd have basically diamonds synthesized from graphene made out of carbon-14. You could even sandwich in layers of insulator, you know, like a silicone or a you know like a alumina, you know, something, and then create, like, you know, nuclear batteries at the nanoscale that are as strong as diamond, and you can never break them. You know, I mean, they last for, you know, 10,000 years or whatever. And that's just upping the amount of energy from the Brownian motion by adding the extra beta decay, you know, and then tapping into the Brownian motion plus beta decay. Amazing.
So yeah, thanks for your answers. I appreciate it.
I'll ask a question.
I'm sorry. No, it's my fault. Sorry, I was getting more coffee. And Jean has her hand up too, but yeah, go for it. Go for it, Josh.
Oh, okay. About, I don't know, like 10 years ago, maybe a little over 10 years ago, I was reading about some battery technology where they were actually using artificial diamonds and I think nuclear waste or some sort of nuclear material. Is that at all related to some of your research?
Yeah, it's what you're talking about. They're using carbon-14. Carbon-14 just is there's a waste amount of carbon-14 that is created in nuclear reactors from just, you know, the nitrogen that is just exposed to the neutron radiation from the reactor and then becomes carbon-14, you know, so that material, because it's more concentrated than background, has to be disposed of. And it's like when they throw away gloves or whatever else, I mean, that has a very small amount of, you know, radioactive material on it. But for a practical purpose, are you going to want to try to enrich carbon-14 to a usable level from nuclear waste, or are you going to want to synthesize it directly so that you know exactly how much you got? And, you know, that's the thing. Most people, myself included, you know, that are just interested in advancing science, not so much thinking about the business side of it. You know, we see something and we're like, hey, it's possible, let's do this. But the business people are looking at it like, yeah, it's possible, but, you know, how am I going to make a buck out of it? You know, and that's where it all basically comes back to. All of us bouncing around here in normal reality, we have to realize that if someone can't make money out of what we're doing, then they're not going to be interested in doing much more than talking to us. Like, that was an interesting conversation, but that's about as far as it'll ever go.
So let me go to Ms. Jean Manning. Jean, welcome to APEC. Can I get you to turn your camera on?
Thank you.
Jean, thank you for joining us. You are a celebrity in your own right. So
The Jean Manning is
the
here.
Jean Manning, yes.
Well,
Well,
I am intimidated by all the technical knowledge in this group, but I'm lurking on these because I learn so much. I just addicted to learning, I guess. And anyway, Michael, I want to ask a layperson's level question, if I could. And first, I really appreciate your responsible attitude, and actually the attitude of everyone here is wanting to advance science rather than it's not as important to make a buck. So my question goes back in the history because you've gone back a way, obviously. Does Paul Brown's story fit into the history of all this line of research? Did he make advance in the state of the art, or are you too young to remember Paul Brown's story?
oh no, I remember Paul Brown. Yeah, of course.
Yeah. Well, I know. Yeah.
Definitely one of the people that got me interested in learning about science.
Paul Brown built an SEG too, if I remember right.
Yes.
Yeah.
Okay.
And as I recall, he had results with it. And this is a little bit off topic, but from what I remember, Paul Brown built an SEG. He got it up to speed. He made the thing work, and actually the neodymium caught fire. That was the story that I remember reading.
Well, I'm just wondering if because he was going for big effects with his photovoltaics and resonant nuclear battery, and so is that why he was harassed?
You're asking me to assume something of an unknown, so but I would respond that I looked at the plight that he had faced, and it was a caution tale for me. I haven't had as much of a issue with the government as a lot of the people that I have dealt with have. That probably has more to do with the fact that I'm a little bit more known to the government than most of the people that I was dealing with, simply because military background and my dad being ex-military, we're kind of known, to the government. So because they had a lot of pre-knowledge of who I am and what I'm about, I didn't have to deal with as much of an unknown factor as other people have. And I didn't know that on the front end. I found out about it on the back end, because my dad worked at the Pentagon. I mean, he was not a big important person. He was just a courier, for the Air Force during the Vietnam War. But he rowed a boat, to the, down the Potomac to go to his office at the Pentagon, So he was not an unknown to them, is what I'm saying. And me being military and then later on a contractor, I'm a known person to them. So they already knew what I was doing. So they actually looked harder at the people I was talking to than they did at me. Like, I had one person back when I was first talking about the UFO Technology Hackers Manual, and was doing radio talk shows long before I even knew Tim Ventura. I did some with him as well, fairly late in the game as far as when I began to become involved with that. But when I was doing like sightings on the radio and the X Factor and, you know, some of those things back in the late 90s, I would like send somebody some mail. You know, we'd have a correspondence, and then men in black would show up and, you know, arrest his mail, you know, to find out what I had sent to him, you know, because they, you know, and it was disturbing to him to the point where he cut off contact with me. You know, I mean, it was like, but that happened a few times, but it's also had some positive effects for me, at least, as far as advancing my knowledge. I was able, like back when I was president of Beta-Voltaic Industries, Inc., I went to Oak Ridge National Laboratories and I spoke with them about stimulated beta decay. And this conversation was going to last, perhaps, they had slated 30 minutes for the conversation at Oak Ridge, and it ended up going over an hour and a half. Just, you know, 30-minute presentation, an hour of Q&A, and then 2 hours later, we were all basically starving and had to go to lunch, you know. But that was probably had a lot to do with the fact that, you know, they were comfortable with me as far as, you know, I was a known factor. And I guess that probably has a lot to do with a lot of us. It's not what you know as much as who you know.
Well, thank you.
That's good to speak with you. I've read you and listened to you for a long time.
Yeah,
Good-
absolutely.
with you.
Gene, thank you for speaking up. Gene, we would love to have you speak and present at some point as well, if you're open to it.
I don't have
Not,
anything to say that you don't already know.
I know, but yes, I will probably continue to beg and grovel though. So just
I
be
will continue
forewarned.
to lurk on these forums.
Okay. Well, thank you. So let me see. Let's go back and see who else has questions for Michael McDonnough. It's 3 p.m.
Oh goodness.
Yeah, we're doing pretty good. 3 p.m. Pacific. And if we don't have any questions, I might see if Todd Desiato could go now.
I have a question.
Yeah, go for it, Al.
Yes. Regarding the potassium, I think it was like what, 97% percentage of purity, I think. Is that like this is for Michael McDonnough, a question to him if he's still on. But
yeah, the volume of the sample.
Yeah, is that like what hertz range is that? Would you estimate that to be in?
I'm sorry. I don't understand the Hertz correlation.
Well, everything's got an oscillatory rate, right? I mean, has certain vibrates of cycles per second, correct? I mean, wouldn't it be vibrating at a certain rate? I mean, I'm just curious.
I don't think Michael probably wouldn't know that offhand. Yeah, I mean, atoms all have resonant frequencies and stuff, but he probably.
The only thing I'm aware of as with reference to frequency and that particular isotope, it has to do with the spectral lines that it produces under, whenever it's being hit with a photon.
Okay.
Whenever I'm referencing spectra, I'm speaking specifically about what I saw something come across my screen and got me distracted. I'm sorry.
But you're talking about like the EM spectral line.
Oh, it was
right?
Atlantis Rising. Yeah. Okay. I saw that. Oh, yeah. Whenever I'm talking about the spectra, it's the light spectra that it gives off whenever it's stimulated, with a photon. So it's like, it's a photospectra photospectra is what I was referencing. As far as its resonant frequency of the molecule, is that what you're? I mean, I'm trying to.
Yeah,
trying to
yeah, the
understand your
resonant
question.
frequency of the volume 97% potassium, basically. But yeah,
Okay,
I
that
mean,
that specifically that reference, the 97%, that was of a sample that was provided to the SEM, which was the the scanning electron microscope. The percentage of the the quantifiable part and the qualifiable part, it was potassium 40 was 97% of the sample, and that was of that particular sample under the photospectra that it was given off. And I think in the SEM they're using what, X-ray spectroscopy, so that was under X-ray spectroscopy. That was basically what you get when you bounce a particular frequency of X-ray off of it.
okay, that helps. And I think that virtual photons would be higher than that potassium thing, correct?
Well, virtual photons don't give a frequency. I mean, virtual photons are only pulled into a frequency range, like momentarily, or they bind and then they become active, like with the, like a electron positron type of reaction, for instance.
Oh,
That was one
okay.
of the things that really interested me in potassium 40 was potassium 40 is the only isotope I've ever seen that gives off an equal amount of matter and antimatter in the form of positron and electrons. So, and that's a curious part about how it's synthesized, is that because it is created in a supernova explosion, it is composed of both matter and antimatter electrons that have hit the that have created that particular isotope in the plasma vortex rings that are compressed from the star disintegrating.
Okay. I just wanted to add in the cells of the body, like, or the microtubules, I think it's the microtubules. They said that there's a phosphorus line in the cell, or and I think in the microtubule, either a cell or microtubule. There's a phosphorus line that is able to touch, say, quote unquote, touch the light. So it would touch, I guess, the photons, or maybe the gamma photons, or like within that range. If you're just going through the photonic light, like X-rays, gammas, and then in that section.
In the
And
visible spectra, or in the photon spectra.
Yeah, in this photon spectrum. And I wonder if that photon area where the phosphorus creates like an extra dimension, of its own inside the cell, where it's able to hold that light close to, because like they said that the phosphorus goes from that cell or microtubule, I don't know which one it is, the whole cell ceases to exist. But it says that it creates certain components very high in that energy to hold the light before it would go into the virtual photon state. And I wonder if that is next to the potassium 97% volume in energy. So I was just trying to reference that, tie the two together. If that's cell was made of potassium, or if the phosphorus was made potassium in the center of it, and it's glowing, right? It made a light. So, but you can look this up. It's been done in 2016. Like they found microtubules in the light. Light in the microtubules. So and I did further research about the phosphorus. So I'm doing a project on my own right now that's kind of unorthodox. And I'm studying wave components of like wave refractions, and then like back EMF waves that come back and then like would merge on certain superposition points during like say a bucket with water, and you drop water in it and all the waves go and bounce off the barrier back to each other again. and I was trying to trace, all the how the waves would superimpose over a duration on, on a time scale. So, like, how long will it take these waves to reconverge back with the energy that was supposedly lost and then comes back? So, and I was trying to like find some way to like scale all the waves up to a ridiculous hertz range, kind of like an even curve line, where there's you get all the signal loss that you had lost back, or all the frequency, frequency energy that goes, like being mitigated. Like imagine like you have a curve line going up, right? And I'm not making much sense here. What's a good example? Oh,
let me give you a little help here.
Go ahead.
With phosphorus, with reference to phosphorus. Phosphorus is very interesting because it is at the phosphors are at a place where they're intersecting electrons, phonons, and photons. The intersection point of electron, phonon, and photons, that intersection point creates phosphors, which is interesting because it's the only atomic area that has a direct correspondence between phonons and photons, which is why you have a very easy release between electrons converting into photons within the range of the phosphors, within the atomic range of the phosphors. On the periphery edge of phosphors, they have kind of a curl on the edge of the toroidal component, the outer toroidal component of the phosphor is on the atomic level is extremely close between photons and phonons, which an electron can pass through that and discharge either way. So it can either create a photon or it can create a photon and a phonon, or it can create both. That's why phosphors are so energetic, with electrons and light. Like for instance, phosphors can get a very small amount of photons in the UV spectra, which is a very high spectra, very tight spectra. And because of the frequency range that of that particular set, that frequency range of photons in the UV spectra is very, very compact. It's very close to the phonon spectrum. And in the outer shell of the outer electron shell of the phosphor electron of the electron cloud around the phosphor atoms, it can go either way or both, which is why phosphors are so energetic. And so it's difficult to explain the correlation between photons, phonons, and electrons in phosphors because it's not something straight. It's multidimensional. It's fractal in 360 degrees, which is difficult for human brains to process. I mean, it's a lot easier for us to our brains are kind of more focused on like acquiring a target and hitting a target, like if we punch something or hit something or shoot something or, whatever, if we grab something, our brain is able to, to do that very well. But whenever it comes to fractals and things going different directions that we're not able to perceive, in the 1, 2, 3 line, what I call the 1, 2, 3 line, which is you have left and right hemispheres in the center. Anything beyond the 1, 2, 3 line is a bit perplexing for human beings, to grasp. So when things at the atomic or subatomic level happen beyond the threes, positive, negative, and neutral, it's difficult for us to put a formula to it or to grasp it, because it happens in so many different dimensions at the same time. We don't have a way to follow it with our 1, 2, 3 brain. Does that make sense to you?
Yes. What I had an idea of, like, so if it's fractal based dimensional, like, say it's superposition of particles, right? Where it's everything at the same time, right? When in that state.
Yeah, in a fractal, you have the strange attract. You have the attractor, the
Yeah.
neutral, and but what's difficult, I mean, it's easy for us to look at a fractal on a 2-dimensional. It's really, really hard for us to look at a fractal on a multidimensional. It's practically impossible for our brains to compute.
Well, Michael, if I could jump in real quick. So if folks wanted, you spoke last session about the plasma volt technology, and you're talking today about beta voltaics. If people wanted to build one of these, if they wanted to participate, I guess the first thing would be, how could they reach you? Can they do email?
Yeah, of course.
Okay.
Or you can go through my website, plasmavortexfusion.com. And it's Michael McDonough at plasmavortexfusion.com.
And then it's the Remington Ventures, right?
Yeah, remingtonventures@gmail.com.
Okay. Yeah. So those are both emails. And yeah, I can paste. Let me paste that into chat. And then how difficult do you think it would be, again, if someone wanted to build, because I met someone who did try and build one of these with americium, a beta voltaic cell, and I saw results from it, actually. But
yeah,
how difficult do you think?
And you still have children.
I still have children. Yes, he had it inside of a lead enclosure. So
I know. I'm just being funny.
Yeah. Yeah. Well, and I should be forthright about that. So right around the time that I met you, I used to know a fellow named Merlin Della Ryan, and he had a lab where he was building stuff. And I mentioned to him that I was talking to you, and he said, "Oh yeah, I got one of those." And I was like, "Okay, I've never heard of this before." So he pulls out this contraption. He had a bunch of americium pellets in it, and I believe that's an alpha emitter, not a beta emitter, but I believe it was doing
alpha.
Yeah, I believe it was. I think it was doing like a scatter, right, where it was hitting the container and generating the voltage that way. So he puts this thing on the scope and he turns it on. He said, "Okay, here's with no pellets in it, right? With none of the americium." He's like, "Here's what it looks like when it's with nothing in it." He did the scope trace on it, and then he's like, he puts the pellets in it, and he's like, "Okay, here's what it looks like on the scope with the pellets in it." Does the scope trace. Then he said, "Now I'm going to turn it on." He turns it on, and sure enough, it generated a voltage, and it wound down really slowly, like it was self-generating a current. So for me, that sold me on the idea right there.
Well,
his was different. It was not the same model you're using. Yours is cleaner and more powerful, but I mean, his was more of a proof kind of a thing.
May I add anything?
Yeah, go for it, sir.
Yeah. Well, there was a guy named Anirban, or ANIRBAN. I can't remember his last name. It's an Indian name. It's very unique. But he was experimenting on something called a nano brain. You can Google and YouTube. I'm not. You can YouTube it and put like nano brain. Using I'm trying to remember, using time crystal as something like that. So he made like this nano machine, at nano level, and like it's weird, like fractal based computerized information system that like was accessed in, like, I guess the time dimensional frequency section, because Google had made time crystals before in the quantum computing or whatever, and he supposedly accessed that range of power and frequency and produced really weird effects with this nano computer organoid thing he had created. So he has a book. Yeah, he has a book out that you can buy on a PDF file or whatever. You would just have to Google it and this information. I got the book, but it's more like a video thing. So you pause it, and so I'm reading it right now. And he has a different technique for what interests me for Fourier analysis than Fourier analysis or other types of ways to scan frequency, amplitudes, and crests. And he uses fractals, and he used something called the prime phased metric, he called it. And like he put the fractals with the prime numbers like 235, 235 and like 7, and let it like generate on its own to like map out the all the frequencies of and all possible variations in the prime numbers. Like I know that sounds like very esoteric or something, but that's what he said he used in his book. There's more to it. Probably have to read, but you can check it out and see if that it can be applicable to anything. I mean, if it's in the time frequency domain, as far as like time travel, like that's pretty awesome. Because like the smaller you get in wavelengths, the more you can mess with stuff. I heard there was a guy on I think it was Versadium YouTube channel, or somebody said that the gamma rays distort time, cause time distortions, right? So I would think that he used a hertz range that was higher than gamma rays. So as far as in his nano brain, so he's probably messing more with just time distortion. Like he was in the time section, but he was a lot higher energy, so it must have been multiple timelines. That's a guess, but you can check it.
Yeah. Well, Michael, would you like to respond to that? Todd just messaged me and he's ready to go. So if you have any thoughts on that, let's wrap it up with that, and then we'll squeeze Todd in.
On what he just said?
Yeah, on L's thoughts.
I don't have any knowledge about time frequencies, or excuse me, time crystals.
Yeah.
Now, when you talk about fractals, one of the things I do like to tell people is it's not fractals on paper. Fractals in the universe happen in every direction all at the same time. I know that's impossible for you to think of in your brain because it's impossible for me to think of. But fractals don't just happen on 2 dimensions, they happen in multi-dimensions. And when you start to think about how that operates, it's a good idea to read my book, that one that I gave you to put up on your website.
Yeah, and that's up on the conference notes.
Yeah. Anyway, that particular one, I go into that a little more about how the fractals can work in multi-dimensions, and I'm giving a little bit of substance to that in the book.
Okay. Well, let me do this then. I want to thank you to everyone, and Michael, thank you especially, sir. Let's give Michael a big hand. Thank you for a wonderful second presentation and Q&A. You've given people a lot of material to chew on, and so the remingtonventures@gmail.com, that's the one that I use. Plasmavortexfusion.com, that link is in chat. So I would say if you guys want to contact Michael, please do that. What I want to do now is I want to go to Mr. Todd Desiato. Todd is around. There we go.